talking about applying new technologies to old areas, relative geologic time, Wheeler diagrams, and emphasis on faulted plays, growth faults and expansion faults. And the basic idea was in the late 70s, when I started in the business, the Exxon people came out with sequence stratigraphy. And it was great, and it tied eustatic and sea level changes and sedimentation and subsidence into facies, and everyone here knows all about sequence stratigraphy. And about the same time became apparent that Wheeler diagrams, which are about 60 years old, suddenly became front and center for understanding the distribution of facies in time and space. And the idea of facies diagrams and sequence stratigraphy is to take cross sections in depth and transform them into relative geologic time. This is from a very, very smart guy named Fourier. He works with DGB, and he writes a lot about Wheeler diagrams. If you want to read about it, that's where you want to read. And so I started working at Mobil Oil, and I started doing what everybody wanted to do about those times. I wanted to map out top laps and on laps and off laps and down laps and break out different sequences and do seismic stratigraphy. That's what I wanted to do. The only problem was I was working Gulf of Mexico up on the shelf and onshore, and as many of you may have noticed, you could look as much as you want, and there just aren't on laps and down laps and off laps. And it was a real problem. And I don't know if many of you had the same frustration as I did, but I just couldn't find them. And it started me thinking, what's going on here? This is the revolution in stratigraphy, and I can't get on the bus. And as I thought about it, I said, well, why are there on laps and off laps and all that are a response to eustacy? And the answer is pretty simple. You have stable platforms where all this work was done, and for stable platforms, Wheeler diagrams, which is on the bottom here, transforms everything from depth into geologic time, and you can see what's going on, and it all makes a lot of sense. And one way to describe a stable platform is, well, they're like hinges in a way, and as you get more proximal, the amount of subsidence and accommodation isn't much, and as you get deeper water, you rotate out in a pretty predictable way. And so I thought, well, what happens if instead of the stable margins where Vail and Mitchum and all those people did their work, we talked about the Gulf of Mexico, where we don't have a stable platform. We have salt withdrawal, we have growth faults, and there, instead of this type of situation where you have subsidence, those little arrows increase as you get more distal, and the sea level change will at some point match the subsidence, and that's kind of where you're getting your definition of where the shoreline is. If instead, question is, what happens to the on-lap and off-lap pattern here? And the answer is, well, you still have on-lap and off-lap, but the problem is it's no longer on the underlying geology, it's against the fault plane. And so I got all excited by this. I was at BHP at the time, and I came and I presented this at the 1990 and 91. There was a GCS SCPM conference. Were any of you there? It was, hey, there you go, one person. Oh God, I'm dying. Hey, two. And it was great. It was the first real conference on sequence stratigraphy and exploration. And I explained that that the sequences, which are easy to find with on-lap and down-lap, are not so easy to find in growth faults like we have here in the Gulf of Mexico. And the reason is obvious. There are no geometrical irregularities like you're looking for. And this is a real problem. For those of you in the audience that have spent their career slipping logs and chasing oil and gas, I'll bet you anything there was an area where you found a fault at kind of the same stratigraphic level. It was missing section on the log, and no, it wasn't. It was probably an unconformity, like this McCullough paper showed on the down-thrown side there, a bunch of extra section. And so the question is, okay, well, the Exxon people look for on-laps and down-laps. What do we have to do in the Gulf of Mexico? And the answer is, well, you've got to find the missing section. And the best way to do it is you slip your logs, or you go ahead and you take your seismic polygons and you slip them and you find where there's extra data. And in a very simplistic way here, you can make an expansion profile. Well, every fault didn't exist, and then it started existing, so it went from 0 to something. And every fault pretty much died, gets buried. And in between, the fault has a big expansion, and so the expansion profile describes the missing section, which is the mysterious missing unicorn of the Valian school of sequence stratigraphy. And it gets more interesting than that. If you look at expansion profiles across growth faults, when you think it through, you do have a history of the relative coastal onlap buried in that expansion profile. Let me explain it. If we take a look at this very simplistic profile for this example, well, that's what it looks like. And at a particular snapshot in time, you had about 15 feet of sediment on the upthrown side, 20 feet on the downthrown, maybe a 25% expansion, and that makes sense. What happens if sea level rose? If sea level rose, then that ratio becomes 10 to 20 to 25, and that simple expansion profile gets a little ripple in it, and that ripple goes the other way when the sea level drops. And so, one of the things that became obvious after I did this work was that when you make an expansion profile, even of a real simple fault that just seems to be growing gradually, you get this high frequency ripple. And that high frequency ripple is a record of sea level change that's buried in the expansion profile. And one way, if you want to get philosophical about it, is that an expansion profile of a typical growth fault records the eustatic history much like a radio signal records music. Kind of interesting. And so sequence stratigraphy means picking sequence boundaries. Picking sequence boundaries around growth faults is tough, and mostly, what on earth does this have to do with the Wheeler diagrams and relative geologic time, which is what the reason I'm here talking. And the answer is a little bit counterintuitive, and the answer is that if you can make a Wheeler diagram in precision, very precise from seismic data, you have also made an expansion profile. And then the Wheeler diagrams, which you can make with the modern software, and there are several companies. What I'm talking about and showing, I use Paleoscan, which I know some of you have. We have Nana Hemstra from DGB. They have their own software that does that, and there are other companies. And so, but there are places now that can make Wheeler diagrams, and I'm going to show you what that is. So this is how you do a Wheeler diagram on 3D seismic data. You take your regular seismic data, which is in depth or time, and you go ahead and specify at every level what is the geologic time with the help of the computer, and then you can reformat it and transform it into a Wheeler diagram. That's the first step for turning a Wheeler diagram into an expansion profile. And again, this is not an academic exercise. If you have an expansion profile, you can break out your sequences and do better exploration. So the second step is, now that I know where every particular marker and horizon is, how do I go ahead and take that and compare the expansion. When you make Wheeler diagrams, the various software manufacturers have made it very simple to answer that question. You simply create an attribute that shows you what the thickening or thinning is for the various levels. And then putting it all together, what it is, and this is a slide that just shows what I reviewed. You start with a regular piece of geology, and the first thing you do is you convert it to Wheeler space. So every reflector is flat, and that's the way it is. Next, you make an attribute on both fault blocks, and this tells you how the various levels thicken or thin, and that's related to the divergence of the reflectors. And then finally, what you do is you take a comparison on both the upthrown and downthrown sides. That comparison is an expansion profile, and as I showed, if you detrend that, you go from your combined expansion profile, you pull out the structural component, and voila, you have you used to see. I know it's a bit kind of unusual to look at things like that, but the bottom line is this, is that if you can go ahead and come up with the same type of work, and this was done by University of South Carolina, Professor Kendall over there. It's on the SEPM site, a lot of good stuff there if you want to go see it. If you can see that here, everything is oriented on his sequence stratigraphic presentation by the U-static level, what if I can extract that in offshore Louisiana? Will that help me in my exploration, in my breakout of sequence stratigraphy? And the answer is yes. Just like on this, I can see there's a cross-section. Well, here's a cross-section of the geology. And over here, I can see the facies. And remember, that's time-stepping, and I'm time-stepping too. I flattened it on a particular horizon. And over here, you can see what the accommodation space is, because it's the distance from the sea bottom to the surface of the water. And over here, looking at some of the attributes, I can come up with a very good understanding of what the accommodation space is. So what does it get you? This is pretty fast, but if you start looking through this and it's looping, it gets you several interesting things. Here you can see a seismic line, an east-west line, and this is the accommodation space that's changing. It's a salt tectonic influenced area. Over here are the different facies, roughly analogous to that, and at the top of the accommodation space. So, taking a breath, what we're doing is we're mapping every level, and by mapping every level, we're being able to, in a really kind of interesting way, reproduce what academia has been doing, except with actual seismic data. And so that's kind of the background. And now I want to talk a little bit about the workflow that goes into it, because that's pretty important. And then I'll tie it together at the end. So I'm working on a public domain data set that is from present-day Louisiana shelf slope break. So it's all above salt, what I'm looking at. And the workflow is what I want to go over now to give you a feel for the new types of approaches to exploration in the Gulf of Mexico based on this type of technology. And as I said, we have some representatives from the leading software companies here. Starting off, how does it do all this stuff, Because if you read my abstract, in my abstract for the talk, I said, we spend tens of millions of dollars on seismic, millions on processing it, and a lot of money on interpreting it, and then at the end of the day, you have the top of this reservoir, the base of that reservoir, the seal, the top of pressure, and the other 98% of the geology is unmapped. And do you need even to do it? And the answer is yes, you need to. And here's what they do. These software does some real basic stuff. Anything that can be auto-tracked, it auto-tracks. End of story. It auto-tracks it, it comes up to the faults, it stops, gets to rough areas, it stops. It's your job to make it continue. How do you do it? And different companies do it a little differently, but you pick and create a geomodel, and you're actually developing a geomodel that is going to be through the entire 3D volume. Every peak, every trough is picked. And then from that, you have your basic layering, and from the layering, you can break out different sequences. And that's the first step for going into a very integrated stratigraphic exploration approach. And weaving it together is very important in faulted areas, but there's a kind of an 800-pound gorilla in the room. And what that gorilla is that it's garbage in, garbage out. If you don't correlate exactly right, then your Wheeler diagram and everything you do is not going to work right. And so I want to walk through with you why the usual procedure of interpreting seismic and logs and putting them together is about to be superseded by a pretty exciting new approach on doing it. So no matter who you are or what software you use, you have to jump that fault to figure out what's going on. And so how do you do it? You correlate. And everybody's been doing it. You do it with logs, you do it with seismic. Ideally, you do them both. And so you correlate, and as you correlate deeper and deeper, you see that there's more and more expansion. That's what those red lines are. And then you come down here, and now you're not so sure where you are. Maybe that's the correlation. Maybe it expanded more. Maybe it expanded even more. You're just not sure. But you gotta solve it. And you have to solve this to do a good job with the Wheeler. Well, one of the things that's changing with the technologies, and a lot of the larger companies are using this technology, the small companies not so much, is that once you start auto-picking everything, you can change the chronology, and pretty much as you start picking your logs and seismic, you've got your finished maps in front of you. And so what I'm doing here is I'm taking that mouse down on that line. These are the same lines, by the way. And as I take that mouse down, you can see that it says at that particular level, the machine can auto-track this big. And sometimes it's very large and sometimes it's not. And as an example, I went on the line on the right and did the same thing. And those might be little patches or little mini maps, and they might be big. You don't know. Well, what's pretty much a game changer here, I think, is that in addition to just making those little maps, the various companies are now making the seismic attributes. So imagine you have a log, you have no idea what's going on, there's a sand, and you take a look at that and you can take that sand and realize at this level it's going in this direction, and that helps you with the correlation. And so, for example, here let's apply this type of new technology to stratigraphic exploration. That looks like a good fit, or maybe the one above it. You know, which one fits? These days, I would sit there and do that again and again on different lines, but when you have this type of kind of artificial intelligence aided mapping, you can see right away that this looks much more geologic than that. And so when you have your maps for your initial interpretation, you can start using geologic common sense and intuition and very rapidly put together a chronostratigraphic surface that matches that well and the other wells and makes sense with the seismic geomorphology. That's a game changer to me. Usually, most everyone here who's an interpreter, you make your maps and kind of when you finish, you make your attributes. And this reverses the chronology. And so once you do that, you can say, well, man, I got something going. I can then datum everything like I've done up there. And you can see on the left and the right, there's little bright spots, and because it's flat and it's a big area, and maybe this geology is the same as that. And you get a sense that maybe your sub-regional understanding is improved. Well, in fact, there are other attributes that you now have that you never had before. For example, right now, we can look at the accommodation space that existed at the time of deposition by the divergence of the reflectors. And this is saying, well, hold on a second, the geology here was very different. I've got, in this slide, the red means it was pretty deep and you had a lot of accommodation space. And you go, well, what's going on? And what's going on is that if you look under that area, you have, you can see that unconformity over there. Unconformity is in the wrong spot, makes no sense. How do you have a deep cutting unconformity in a low? And the answer was the salt was up. The salt was up, you had some domal feature that was cut, and then the salt came down, and that gave you a long-lasting accommodation space. And so maybe a little too much detail, but the point is when you bring together all these things, you get the idea that you can put together the stratigraphy as you're picking it. So let's start talking about logs, because here, you know, with all the millions of logs, any seismic stratigraphy has to be integrated. And so when you look at a lot of logs around growth faults, you might find that things are pretty buried up shallow, and then you expand quite a bit. And the question is, how do you go ahead and do the correlation across the faults in situations like that? Well, here again, I'm using the machine, which is auto-picked everything. It's coming up, and it's saying, I can't get across the fault. There's no way, and neither can you, until you get pretty shallow. And as always happens, the fault gets a little buried, and once that happens, you create or recognize the work that's already been done for you, a chronostratigraphic surface like this, and you say, okay, so that's my datum, I know where I am. And now, people that have worked Gulf of Mexico a long time know there are tricks to mapping expansion faults, and those are the relays that you'll see everywhere. These faults don't go forever, so instead of correlating across, you try to go around them. And if you do that well, what you can do is, as this shows, you would start over here and start moving up on the map that was made already, and you can see that little fault over to the left. As you get higher and higher, that fault kind of goes away, and then what you're going to do is come down this dashed line over here and follow this around, and you have your maps when you start mapping, and your correlations become much easier to do. And there are different software vendors that do it. That's kind of the new stratigraphic exploration. It's correlating real time up front with maps that were made for you. Now, a lot of people say, oh, come on, man. I remember computer contouring when it first came out. I personally know somebody who was fired for using computer contour map at a presentation, you know. But here it's different, because what you're doing is you're aiding things. You bring in your logs, like always. If you want to tie your logs with seismic, you need to normalize your logs to solve the problems. And it's very, very important. Can't get away from it. You've just got to do a lot of good synthetic matching. But once you do, and here this is kind of an important part of this whole talk, you have your markers in your geology. You're tied to your well, and right up front, at every single level from shallow to deep, you have your seismic horizon kind of finished already, and they can talk to each other. And it's a very iterative process, because remember, when you're trying to put everything together, you have log picks and you can get lost. You have horizons, and sometimes you don't know where they are, and the time to depth and the velocities. But when everything works together and you have everything in front of you, you can actually go ahead and do a lot of work that makes a lot more sense. And so, moving on to real-world examples of what that means, what you want to do is go ahead, and how many times have we all looked at logs and log character saying, I don't know what that facies is, I don't know what it means. Imagine if top to bottom of your log, you can come in and pick the log and immediately see what level you're at and what the facies distribution is associated with that log. That's a different way of doing stratigraphic exploration. That's a very integrated way. One of the things that's very important is you have to have the bathymetry in the data you're doing. And one of the things I do is I take bathymetric data and I turn it into a well log, and then I'll come in and create a volume, and that's you can see the maps above showing you where you are on this data volume. And I'm looking at the different bathymetric zones that I'm integrating with my log picks and my seismic. And that type of stratigraphic integration is something new. It's pretty much, it's a new thing. One of the things when you have everything integrated like that, you can start looking at type logs and asking questions such as, I have a maximum flooding surface. What's the big picture? What's going on here? And then you would, first of all, remember you've time-stepped every bit of geology, and so you know what the character is. You know what the attribute is. Well, that's pretty monotonous. And then you say, what about the accommodation space? Well, as you expect, it's a kind of deep water that's zone 5. That's bathyal, as the top one shows you. And so maximum flooding surface is what you expect. Not a lot of granularity, not terribly interesting. However, there are times when you have a sand and you don't know what's going on. Where does that go? And you move that sand up and down, and that changes the datum here, and it changes what you're seeing. So what's this sand all about? Well, this is inner to middle neritic. Your water depths are certainly less than 300 feet here. The blue up there shows you a lot of accommodation space. And so you can see the well is right on the edge of the very deep accommodation and a more shelfal area. And this is showing you, orange, you've probably got much higher sand content based on the inversion data here. And you look at it all together, I have my echozonation, I have my accommodation space, I have what's probably lithology, and then I have my seismic character. And you do this level after level after level. So what does it get you by mapping out every single level? Is you can start exploring every single level with a granularity you couldn't do before because you had to be kind of focused on what you were looking at. And that's the technology that is coming our way right now, and I think we're all perfectly well suited to handling it because of the years of experience of trying to do this mentally more than anything else. And so if I just go back once more here and look at the top one, that's really interesting. The blue represents where there are small mini basins opening up and sand dumps. And if you didn't know that, and if you didn't know the rapid variation due to salt movement in this area, you might mistakenly try to correlate sands that don't need to be correlated. And in fact, and I showed you this one already, the salt movement and deflations are very well tied to what we're doing here. If you're chasing subsalt and you're looking for subtle salt welds, you had best start looking at the stuff above salt to understand that type of thing. What does a high stand systems track look like? If we zoom out here, this is one of the many, many, many levels of fascinating facies. By the way, this data I got from the USGS. This data is a little bit older than my oldest daughter, you know. It's getting on to 30 years. And my point here is 3D. 3D data. Yeah, you can get this stuff for free. It's kind of cool. And of course, I can't show the stuff I do in my day job. You can't do that. But the reason I raise that here is because what we're looking at has nothing to do with the high technology of the guys with the pointed hats who do the cluster array processing. This is geology, doing geology in a different way, and I think that's really important. So if you look at this shelf edge delta, that's what it is. I mean, you can see it, and that's one of these many, many levels we're looking at. And you say, okay, so now I know what that sand is. I know what it looks like geophysically. I know what the sand contents look like in close up, and I know the zone, the ecological zone. Let's go back, and I know pretty much that the salt in this area is not well behaved. Sometimes it drops out quickly, boom, and sometimes it doesn't. And if you're doing regional geology and you don't have the insight to look at the change of velocity of accommodation, you're not fully grasping what's going on. That's why I think this type of thing is a bit of a game changer. And so I'm going to start tying it all together. I started talking about relative sea level curves and used to see. And so what we were just looking at is a hole in the ground over here and a delta up there. And let's see if we can pull out the sea level history from that in a way. And so here is the area that I'm looking at. I know from the paleo, it's zone 3, middle neritic, 60 to 300 feet. And so I have, and this attribute shows the thickening and the thinning. This is regular seismic with the attribute. That's where I want to be, and so I'm going to use Wheeler transforms and get there. Geophysicists talk about Fourier transforms and Wavelet transforms. Geologists are going to have to start talking about Wheeler transforms. I think it's that profound. I do. I think it's, and we have one person here, Nana Hemster, who actually wrote a paper or two on the stuff, so ask him questions later. And so when you look at this, you go, how do I get the sea level history out of here? Well, like I explained before, I say, okay, well, here's the area I'm interested in. That's the high stand systems track. And what I want to do is figure out the expansion profile. There's no fault, that's okay. I'm just going to do a ratio of these two. I'm going to pull out the structural part, and I'm going to look at the relative sea level. And so I did that. The software, this stuff is so leading edge. There's no software to do it. I sat there with a pencil and Excel, and I did it that way, you know. But one of these days it'll be computerized. I pulled out what I think is the structural component, and I got this, and I put together a very rough sea level curve, a relative sea level curve, assuming the accommodation space was filled with sediment. Is that robust? Is that reliable? No, it's not. It's 3D data. You need to do this over and over again. And I never learned Python, so I can't do it. I have to use Excel. And so putting it all together, if you remember, I showed you an anomaly before. And when you put together the Wheeler transform here, and here it is, and you know, just take a look at this. Imagine if these were logs. Have any of you ever heard of double datuming logs? You know, and what you do is when you look at growth faults, you flatten a log, and sometimes people take the bottom if they have a marker down there and they flatten that, and it's like printing a log on elastic paper and just stretching it linearly. Here, you can not double datum, but multiple datum seismic and logs, and get the character that comes across. Do the same thing with the measure of the expansion. And once again, I can see that the bright spot, the seismic amplitude I had over there, corresponds to a very condensed section upthrown. And I know that I'm in zone 5. I'm looking at a low stand systems track here. And so that's what I've done. I've come into the seismic and I said this is a low stand systems track. And I picked the top and the base based on the eustatic component. And I made a map. And the map shows me that's what it looks like over here. That's the fault. There's nothing on the upthrown side. This is all low stand stuff on the downthrown. And what's really interesting is if you get away from maps and you say, let's do volume exploration, and you take the volume, you put it together a geobody, and you do the same thing, what you find is that was not one thick zone. It was actually 1, 2, 3, 4, 5 major geobodies. And if you're risking them, do I drill it or not? This has a much greater chance of sealing than something that's connected at several levels. So a volume-based geobody approach is where you want to go. And then on top of that, once you have geobodies in your exploration target, which you broke out from sequences, which you broke out from expansion profiles, and so it's a different workflow. Here I did what's called optical stacking, and I brought together the relative amplitude inversion, and you can see the high amplitudes stop at the same down dip limit. Is that an oil-water contact? I don't know. But for the purposes of this lecture, yeah, it is. And so I'm not telling you where it is because it hasn't been drilled, so don't ask. And so compared to a map-based approach where you lump everything together and get a very fuzzy view, something that is not conducive to geomodeling, you take this sequence-based approach, pull out the geobodies, calibrate it to rock physics, and you come up with a much better way to do exploration. And at the end of the day, you put it all together, and you're examining not only that level we just looked at, but 30 and 40 levels above and 75 levels below. It's the essence of exploration. And the reason I say that is that quite too often we go after what we know is there, and we've got blinders on. We don't see what's at different levels that hasn't yet produced. And so the last point I want to make here is to share with you my view that the state of the industry in correlation is dismal. It hasn't progressed in 30 years, 40 years. 30, 40 years ago, people were slipping logs to go from one side of the fault to the other. 30, 40 years ago, people were taking polygons and comparing them across faults. And that's where we are. We're still there. No matter what software you're using, that's how you're doing your stuff. And if someone has a better idea, let me know. But so I think that there is a need in this industry, and I'd love the HGS to be kind of the center of raising awareness of correlating down through growth faults. You reach a certain point, you don't know what's going on. And the correlation from geology A to A and B to B, it's either expanding like this or that, and you don't know. But if you bring in artificial intelligence and the new machine learning technologies, you can figure that out. With artificial intelligence, this is a metric that describes what's going on with the correlation you just made. And there are other metrics. When you're looking at these different mini basins, the speed of expansion is important. The top one shows you the accommodation space that was available when that particular log marker was deposited. Compare that to what you want to correlate here, and you realize that all has to go into the pot. But most important, when I showed you, you can take a look at the attributes on one side of the fault and see what's on the other side. That's image processing. That's facial recognition. The technology is there to assist us to do better correlations, because with relative geological time work, if the correlations are no good, it's all garbage. RGT it's kind of like film in a camera, and no one's invented the lenses. I mean, that's where we are. I don't want to get on I'm already on my soapbox, but I really think that's it. When you do Wheeler diagrams and you get that 3D Wheeler volume, process it. Do signal processing and analysis on it. There is a lot of valuable information in finding relay ramps in a systematic manner and applying that with these other things. And of course, the holy grail is to come up with eustatic, quasi-eustatic, or relative sea level charts. That's the, if you have one here and it looks like one there, you're correlated. My point is, you put all this together with some of the machine learning that's out there, I could see years from now the same geologists are needed to guide the machines to do a much better, more universal job of integration and correlation. And so, as I wind up, my kid asked me about this talk, and I said, well, here it is. Everyone starts working early in the morning. Yeah. Well, and then at 5:30, we have a couple of beers, and then we have dinner with a lot of carbs, and then I talk about Wheeler diagrams and expansion profiles and expect everyone to stay awake, So it's a tough day, I understand. But the question is, why do we map every seismic wiggle? Is it defocusing? Is it worthwhile? And the only way to answer that is to really ask another question. Are we really exploring anymore? Or are we in a bit of a cognitive trap? Are we just looking for the stuff that ties the nearest production, and that's all we're looking at? And it's something that's inherent in human nature to kind of go through cubes of data to come up with what you think is there. And there's no better example than Michelangelo, who is attributed to have said, I simply removed all the rock that wasn't David, and there he was. In fact, he didn't say it, but it sounds great. And the fact is, it's in the discarded stuff, in near field exploration, which is something I really enjoy doing. It's in the discarded stuff that the treasures lie. And exploration means embracing the unknown, and you can't embrace what you don't see, which is why, yes, it's very important, if you can, map everything top to down, put it together, and work with it, like I've showed you. And so, in summary, I'd say geoscientists are now empowered. This is not artificial intelligence stuff that takes over. To the contrary, it empowers us to integrate as never before. I think relative geologic time and Wheeler diagrams is the focus we've been missing. It's a focus. I mean, everyone knows it's been there, but as a focus, it's something that's been missing for integrative stratigraphy and exploration. There are two powerful tools, Wheeler diagrams and expansion profiles, and they're very, very closely related. And if there's any one thing that you remember from my rambling tonight, it's that the two are very closely related, and the technology is there to get relative geologic time. Let's turn it into expansion profiles, pull out relative sea level curves, specify sequences, and go find some more oil. Once you do that, you can have geobody-based resource estimates supported by rock physics, and I think that's a very powerful thing. And so, kind of my final statement, in the last few decades, in some ways, geology and geologists a little bit have been eclipsed, unfairly. So, in seismic acquisition, multi-azimuth, ocean bottom seismic techniques and nodes have been very, very important in finding lots and lots of oil and gas. Seismic processing, reverse time migration, full waveform inversion, and everything else, surface-related multiple elimination. This stuff is a game changer. You can see things you never saw before. And in seismic inversion, the emphasis on rock physics, extended elastic inversion, joint inversion, and now neural networks is great. But seismic interpretation, we've kind of been left out of that. And I don't think that's fair. And I think the technologies are there now to really turbocharge the geologic-oriented work that needs to be done to find the existing oil and gas near existing fields. And it's Wheeler transforms, which have to be processed. They have to be treated like 3D seismic surveys. Expansion profiles have to be automated and turned into a more robust thing. Correlations, the ability to correlate logs and seismic around a 3D, we're not getting any high-tech support, and there's no reason for that. And as Penny and I were talking about process stratigraphy, that is a wonderful calibration tool that needs to be integrated in here, and all of it guided by geologists. And with that, I'd like to just make some acknowledgments. First of all, to HGS, thank you very, very much for giving me the opportunity to babble like I'm doing tonight. And GCS SCPM, who put on that original sequence strat story back 90 and 91, and was kind enough to give me my paper back, because I lost it over the years, the one I presented. SCPM, wonderful source of things. Eliis, very, very smart people. I work with them, not with them, but I use their software. And also DGB, they were the ones that first started doing all the work on Wheeler diagrams for 3D and different approaches, and I wish them both best of luck. And of course, I'd like to thank the feds for giving me all this data for free. And that's my talk. So thank you very much. questions, be happy to take a shot at it. Yeah.
So, as far as hydrocarbon identification, is anything in the software that you're using help? I mean, you've been doing the stratigraphy, but I mean, does it help you identify hydrocarbon anomalies?
In the sense that hydrocarbon, the rock physics associated with different anomalies changes as you go shallow to deep, and it changes with the facies. And so the best answer, I think, is that if you know for sure where you are in the geologic section, you're continually comparing apples with apples. And if you've normalized your logs and you're using seismic that's amplitude normalized as well, and your geochronology is there, and you know you're not going above an unconformity here, below an unconformity, you go, oh, look at those bright spots, you know where you are. In that sense, it's a very powerful tool for delineating hydrocarbons. But as far as direct detection attributes, that's not it's more of a stratigraphic. Yeah. So the question for those that didn't hear, is there a bridge between the high-tech new techniques and the older one? Yes, I really think this is it. I work with a fellow, and someone, Kevin here, works in the same. I consult to a joint venture. This guy's 75 years old, and he's like a walking encyclopedia of geology, and he understands some new technology, but not all of it. But you got to think intuitively. Someone like that has so much value to add. How do you do it? And then you come in with this. This is an integrator talk I'm giving. It doesn't supersede the type of ability a person like that has. It enhances it. So starting with that one fellow, you say, I can take all your logs in seismic and paleontology, and now we can look at the facies more quickly and more extensively. And that's a message, I think, for the kids, that kids have to, everything in our culture is new. And in fact, we have a wealth of information of people that have been doing this for many, many decades. And a real genuine technology like I'm talking about here grabs that knowledge and grabs that wisdom and doesn't say you didn't know what you were doing anymore, go retire. But we can take that, leverage that with the smart young people who understand a lot of this technology, and together the whole is much greater than the sum of the parts. I think that is the message, really. Yeah. So.
Stratigraphy we have for Steve, a Cretaceous limestone.
Whoa,
complete
awesome.
with torritelli, so you can do some paleobathymetry on this and age control. We're not going to tell you it's a secret chord, but thank you so much for
Okay, well, thank you very much.